So yeah, the talk is finally happening. So happy for that. I'm Rajdeep. So I'm a senior applied scientist in Amazon, and this is a joint work with many people in the team: Ben, Liblit, Yingjun, Omer, Tripp, and Yanjun, Wang. And the title of the talk is User-Assisted Code Query Optimization. So I'm going to talk about a public-facing AWS service, which is called Amazon Code Guru. So Code Guru uses program analysis and machine learning to detect different types of code defects. It's a public-facing service, so it supports different types of scan modes. For example, you can integrate Code Guru as part of your code review process, so it does incremental analysis. It also can do full repository analysis where it scans the code and like makes recommendations. It can also be integrated in CI/CD pipeline. And the language currently that Code Guru supports are Java, Python, and JavaScript, and more language support are in the pipeline in the future. So Code Guru has two components. One is the reviewer, which is a general purpose Code Guru, and another is the security focused. So it supports different integration points with different services. For example, it can be integrated with GitHub, GitLab, Bitbucket, AWS CLI, Visual Studio, IntelliJ, Amazon SageMaker, Jupyter Lab, Amazon Inspector, Code Pipeline, etc., etc. So there are different integration points where this analysis runs today. And it supports different categories of recommendations. So as you can see below, there are security recommendations, input validation, code quality, hard-coded secrets, sensitive data leak, resource leak, concurrency, general Java best practices in Python and JavaScript and so on, as well as AWS best practices. So we launched Code Guru as a public-facing service in 2020. And then recently in 2023, we launched in Reinforce AWS Security, which is about security recommendations in Java, Python, and JavaScript. So let's talk about the overall architecture of Code Guru. So I have made this slide very simplified, but behind the scene, many things like has to work in coordination to make this as a successful program analyzer. So as I said, there are different integration points, GitHub, Gitfarm, Bitbucket, AWS CLI, and so on. So you can imagine we extract the code from there. So there is a compiler in the front end. So for Python, compilers like Pyrite, or for Java, it's Eclipse JDT. So this gives the abstract syntax tree. And then there is some amount of type inference that goes on. So we get code with type annotations. And these are represented in our internal representation language, which is called MU, which is misuse detection graph. So I'll talk a little bit about MU graphs in the later slides. So once the MU graph is constructed from this code, then we build these analyzers, which are in this slide called Code Guru detectors. So these detectors actually detect all sorts of code defects. For example, sensitive information leak, AWS best practice violations, security detections, and so on. And each of these detectors runs with different configurations. So for example, you can say a single detector works as a template which runs on thousands of configurations. So I'll talk a little bit more about what these configurations are. And when the rule runs on some code base, which is basically saying rule is evaluated on an underlying MU graph, it generates a finding. And these findings are basically published in the form of recommendations in during the code review process. So if you look at the snippet below, it's a little small here, but essentially what happens is that when someone raises a code review, it looks at the diff. The diff basically contains the code change. Then it flags detections on some misuse of API through these comments in that code review phase. So this is like overall architecture of the Code Guru service. So let me talk a little bit briefly about the analysis stack. So I talked about MU, which is the intermediate representation, so which we call internally as MU graphs. So given an input program, from the compiler we get the ASTs, we construct the MU graph by resolving names and type information, and each of these MU graph constitutes an MU program. So you can basically, at a high level, you can say MU graph roughly corresponds to a data dependence graph overlaid with control flow and not a control dependence graph. And the control flow here represents the order of execution, and the data flow represents the flow of data along the computation. And next, I'm going to talk about a query language which was built internally. And this is the query language which is used to design most of the code guru detectors, right? And this is internally called as Guru query language. So it's a library or a framework for specifying and evaluating static code checkers in Code Guru. So it has a Java Fluent builder pattern in its interface. And our mission with GQL, so we call in short form GQL. So our mission with GQL is to turn domain experts into analysis builders. So we are a platform, right? And there are different teams in Amazon which has like Java expertise. They are expert in building cloud services, but they want a simple declarative language to write their analyzer. So GQL, so our mission is to turn these domain experts into analysis builders. So what this means is empowering these domain experts to directly specify, then tune, and productionize these microanalyzers to express the different properties of their interest. So for example, determining correct usage of some cryptographic APIs or some machine learning libraries. So what this facilitates is a property specification. So either a human or a rule writer who is a Java expert can write rules like this, or we also have an automatic synthesis pipeline which basically extracts like parses MU graph and synthesizes a GQL rule out of it. So let's take an example. So this is a very simple GQL rule. So each GQL rule has three components: transformers, filters, and matchers. So I don't expect you to understand the graph on the right because it's too tiny. But for the code in the left, this is a snippet of a GQL rule which basically is evaluated on a MU graph which is on the right. So as you can see from the different components of this rule, it has a name, it has a comment, and then the logic of the rule starts with this method called filter. So as I mentioned, this rule basically is evaluated on a MU graph, and each step of the rule that it executes, it collects a match frontier. So with a method called filter, it basically tries to see what are the matching method call, which is named as key set in the MU graph, and it tries to store that in a match frontier. And then basically it checks if the receiver type of that method call is map. Then it sets it in a variable which is called key set call. It's a local variable that you can declare. And then you get a transformer operation on that receiver which takes you to one of the nodes in this graph. And then you can check whether that transformer has a gate call on it and whether the entire thing is wrapped around a loop. So basically in this graph, it's a do-while loop encoding. So with this language syntax, you are checking if there is a key set call of receiver type map on which gate is called, and is this entire operation happening inside loop. And that's how you end this. And then the part before the check operation is called precondition of the rule. The part after the check operation is called the postcondition. So once you save this match frontier in this statement called get call on map in loop, you then check in an interprocedural data flow style whether this key set call is found anywhere in this particular code, right? So this means that now it's going to perform interprocedurally and check whether in any of these methods, starting from this match gate call on map in loop match frontier, if this key set call is being is found in the graph. So you can see like if I am a domain expert and I don't have knowledge of static analysis, what I need to learn is the syntax and the semantics of this language, which allows me to express a complex query like this. So in this particular paper, we talk about the different optimization features in GQL. So the rationale is that when we try to democratize GQL across like different teams in Amazon, we experience that rule authors often encounter like different challenges in writing the rules, and not only challenges in writing rules, but also challenges in evaluating these rules, because often rules can time out, it can be slow, there are memory constraints, there are CPU constraints. So all these different pain points of customers made us think what would be a right abstraction of GQL, so that the rule authors, where we want to democratize this across the different teams, can be able to express these optimizations in their rule without worrying too much about how caching happens or how indexing happens. And this is what we proposed in this paper, which led to the design and implementation of different optimization features in the GQL toolbox, which allowed the rule author to use these different hooks in the language to express their optimization. So in this talk, I'm going to particularly talk about caching, indexing, and customization of analysis scope. Okay, so let's start with a motivating example. So here, we have a rule for this, which we call, like, static analysis is the same as rule, which we call internally. These are GQL rules. And this is a rule that detects pagination error. So as you can see here, this particular API, it's called on a client called S3. S3 is an Amazon service called S3. And a list object is an API that's called on S3. Now, this is a code that is correctly doing pagination, because list object is a pagination error. So when you call the list object once, you get back an iterator or a response object. And because it's a pagination API, you have to keep on calling this API until it basically says that I don't have any more pages to return. If you don't do that, then the rule should detect that and make a recommendation saying that your code is missing pagination. So in this particular case, what happens is that we have an analyzer that, if the code does not produce accurate result, it triggers on this particular code and makes a recommendation. But usually you see this kind of pagination API traits are in the order of thousands across different Amazon services. I have given just one example here, where you see on the right, the template is basically the configuration that we provide to that rule, saying that basically work on an S3 service. So whenever you see an S3 service which has the list object API, which is a pagination API, and furthermore, it has this additional method called on that response object of API, then that code is a safe code. If that's not the case, then that code is not a safe code, right? And we do it in an interprocedural manner. So now the challenge here is that a rule writer who is writing this particular rule consumes thousands of such configurations. This particular configuration is from S3, but the other configuration can be from SNS service, Kinesis service, EC2 service, and so on. So in reality, what made us think is that how can rule writer write rules where they can simply write a rule as a template, but that rule is backed by thousands of configurations. So in this pagination example, in production, in the production setting, this particular configuration can reach of the order of 10,000 entries. And now we have a challenge where a rule consumes 10,000 entries. And now how do you optimize a rule like that, which runs on so many entries? And you have to choose one entry among those 10,000 entries dynamically when the rule actually evaluates on an underlying code. So the brute force iteration over the configuration to identify a matching code entity does not work. So that's why we came up with a new predicate, which is called with rule configuration match filter. So this is a GQL predicate, which allows the rule writer to basically optimize their code in a sense that you first construct an index store. So you build an inversion of the configuration lookup where an index is computed and the code entities, which is the MU graph nodes, are then represented as keys in this particular index. And this enables a constant time lookup, right? So the code on the right is the optimized way of writing a GQL code using this new predicate for indexing into a configuration dynamically when the rule evaluates on the MU graph, compared to the code on the left, which is basically an unoptimized version, which is a brute force way. And we used to have this code in production, but then oftentimes we will have timeouts, right? And the reason timeout existed is because if you look at this particular for loop here, what it is doing is that iterating on all the configs in that missing pagination config. And this is simply a POJO, which is basically a class that defines all the pagination related entities. And it's basically constructing 1,000 different entries of the same rule. And then one among those 1,000 will evaluate on one MU graph, right? So this is a very unoptimized brute force way of iterating, where a simple trick like this, where we take this abstraction from the rule author, we implement this particular predicate, and then the rule author simply express this as part of 3 arguments. One is the configuration item store, which is basically in the indexing. The second is the configuration filter, where they're expressing that this particular node in the MU graph and this config in the missing pagination config should match, their name should match, so this is the filter. And then the third argument is basically the builder, which we use to construct the remaining rule. So this is one optimization which I wanted to show, and this is part of our paper. The second optimization is basically around caching. So let's take this particular example. So let's say here an untrusted user input is read via a get parameter call here, right? So this is the user input. And this reaches the file constructor through the interprocedural call here. So this reaches through this interprocedural call into this file constructor. And this particular flow leads to a path traversal vulnerability, right? So this is one injection error. Let's say another case where there's another injection error in this code, which is called command injection. So this same user input, it flows through this interprocedural flow and it reaches here. And this flow gave rise to command injection vulnerability, right? So this particular code demonstrates that there are 2 different vulnerabilities that exist, path traversal and command injection. And when we allow rule writers to specify rules to detect such errors, we introduce a notion called caching. So here also we abstract that idea from rule authors that if your rule runs this kind of injection checks, how do you share a common forward data flow slices across rules so that every injection rule that runs on this code base does not have to compute it all over again? But if these rules share the same sources, their sinks or sanitizers might be different, but if they share the same sources, they might be able to reuse some of the forward data flow sizes that one rule computes and then being able to share across other rules. So this is essentially the idea of caching here, where injection vulnerabilities are typically modeled as taint problems, where the sourcing reachability is being checked. And the sources are often common across these multiple vulnerability categories, as I showed in the last slide. Now, caching provides a medium to exploit this particular observation, where I showed that if one rule computes a forward data flow slices from starting from the sources, this can be shared across multiple rules. And the way of sharing this is that the caching algorithm underneath does the job for you. So you basically don't have to explicitly share the forward data flow slices, but if the rule writes a statement like with cache dependency, and then it has multiple subrules in it, and if all the rules have this particular predicate, when they're actually run on an MU graph, this particular forward data flow slice would be stored, and then this would be reused across the different rules when it actually runs. So this particular optimization strategy works. So for example, given 2 rules R1 and R2 and 2 subrule SR1 and SR2, they are evaluated on equivalent states. SR1 and SR2 perform the same operation. As I mentioned, like they have to have the same source and the same forward data flow. And SR1 and SR2 both have sufficient analysis budget to complete their evaluation. So which means that every rule also have a budget constraint. So for example, here we have specified this runs in a file scope. Sometimes the rule author can specify that I want my interprocedural analysis or this forward data flow only to be in the package scope, right? So you can become more expressive by specifying how complex your analysis can go, either file scope or method scope or package scope. And if these 3 conditions are met, then the evaluation result due to SR1 in the context of R1 can be reused for SR2 in the context of R2. So this is the notion of caching which we have implemented. So going into the evaluation result, first I want to talk about the configuration in indexing optimization. So here we have chosen 5 AWS best practice rules, and these are rules which basically detect violation of AWS SDK. So we evaluated it on open source GitHub with a time limit of 30 minutes and 5 minutes. So 5 minutes is more realistic time limit which we use for our code review, because often when you submit for code review, if you don't like return back the result within 5 minutes, developers often tend to not like wait too much longer to get back the recommendations from code guru. So this is the ideal time for code review process, but 30 minutes is something where you run packet scan and you get all the detections within 30 minutes. So comparing these two results with indexing, so one is without indexing, one is with indexing. The takeaway here is that if you do indexing and the time limit is small, which is 5 minutes, which is typical in the code review process, rules have more timeouts and less recall. So as you can see here, so here with 30 minutes compared to 5 minutes, you can see the number of findings is exactly the same with indexing, right? And there are no timeouts. But without indexing, we often used to run into timeout issues for a lot of our production rules, and this led to particular optimization which we have used through this predicate in indexing and solve that particular problem. Quickly about the caching experiment. So here we have chosen 7 injection rules, and we have run it across 180 randomly selected GitHub repositories with tented sources. And we use the same time limit of 5 minutes and 30 minutes. So let's look at the results here. So the first result is comparing a file level versus package level. So as I showed you in the previous slide, you can specify the scope of your interprocedural query. So comparing the file level versus package level with a timeout set to 5 minutes, the takeaway is that the file level gives you 8% less findings. It has 1.5x more speed up because it's a file level. The package level tends to be more expensive, and it has 16 less timeouts. So if there is no caching, and this is by the way without caching, where we are comparing file level versus package level. So if there is no caching, the file level analysis perform well in terms of meeting the short time limit without sacrificing too much on the recall. Now let's see how it does with caching. So in this particular slide, I show how the file level and the package level performs with caching enabled. So here, as you can see, with caching enabled, there is no speed up, right, at the with the file level. But there are 37% less findings in the file level, which means that a lot of these injection errors are being captured at the package level. When you set the analysis scope to package level, that's when you find a lot of this data flow analysis, data flow reachability, where starting from the source, you reach a particular sync across the different files in that same package, right? So here, the takeaway is that with caching, the file level analysis reported many fewer findings than package level analysis regardless of the different time limits, which means that for these vulnerability errors, command injection, log injection, we want to do more package level analysis. So to conclude, I'd really like to emphasize that this is a tool which allows hundreds of developers in Amazon to present an interactive approach for rule writing. So you don't have to be a static analysis expert. You can be building cloud services, but these abstractions, these optimizations allows you to write a rule and not only write it, optimize it without knowing under the hood what's happening. So the rule writers can take advantage of caching. They can take advantage of specifying interprocedural queries, either at different levels of granularity, file, method, package, all these different levels. They can scale a rule, writing it as a template and configuring it for thousands of configurations. Taint flow rule is one such case where you can still use configuration because there are usually thousands of taint sources and sinks that are presented to these rules. And thanks to these optimizations, we have significant performance gains, which is like 3x speed up for the configuration indexing optimization and 2x speed up due to the caching. So thank you for your attention.
So do we have any question? Yeah.
So on your initial slide, you also showed the types of vulnerabilities or problems that you detect. Can you maybe go back to it?
Yeah.
So what I'm interested in is there were quite a bunch of different things, and regarding your it was like before that. I think it was like one of the introductory slides. I think.
I see. The was this one?
Yeah.
Okay.
Yeah, you can also see like hard-coded secrets and stuff. And for example, hard-coded secrets are like constants, right, in the code or something. So for this one, your rule language needs to have probably a special rule just or a special component just for specifying that having a constant is a bad thing in this case. I wonder how often do you need to adapt the language in order to allow new rules to be implemented, essentially?
That's a great question, and thanks for calling out the hard-coded credentials here, because that's an outlier in this particular case, because you can find hard-coded credentials in non-source code file, right? And GQL allows you to specify like rules also on non-source code files. So it doesn't have to be Java or Python or JavaScript. So you can write, it's called text-aware custom rule in GQL world, where you can express this kind of hard-coded credential related errors with GQL logic, where it processes a text file. It can be .json, .md, .yaml, .xml, and still be able to express this hard-coded credential like errors. And there are open source tools we are currently evaluating, which is like Credit Sweeper and things like that, where it also detects hard-coded credential and how it compares to GQL. So, but yeah, thanks for asking that question.
Other question? I have one. So the tool that Code Guru is available also for public usage, right?
It has a free trial of 30 days, I believe.
Okay. So I was just wondering if you gave a look about rules written by other people, because if you talk about an Amazon developer, I would say it's not the average developer in the world, because I would expect that there probably the language is misused in many different ways, and maybe your optimization might be more effective, or maybe might even fail because you get something that doesn't make much sense. I don't know.
Oh yeah, I mean GQL is developed by Omer, Tripp in our group, and this often comes up in many conversations with partners as well. So being able to write custom rules, and we are internally developing another language which puts less burden on these builders to express rules, but at the same time like do interprocedural analysis, all this write security related like defects and so on. But for open source, I think Omer always says we still have a path in few years down the line. It's still not clear.
Okay.
So I would quote Omer and say that we still have a path like
I
few
see.
years down the line.
Do you have any comparison with, I don't know if you know SAML, so that was a startup in San Francisco that then got sold to GitHub and Microsoft. Essentially, they're doing something similar in the sense that they allow to write custom rule, but the type of analysis they're doing is really syntactic. So essentially, they take an abstract syntax tree, and you can write a traverse of that syntax tree.
Right. So this is one of the query we had to address in the paper as well. So basically, in SAML, the lack of expressivity of like data flow facts is what constrains the user to write more expressive rules. And this is where GQL comes in, where we don't expect users to know anything about interprocedural analysis, but just know about like the syntax of that predicate that they're using.
Okay.
And that's where we think is the differentiation with SAML. Like, our analysis is on top of MU graph, which is more richer, more semantic, compared to SAML, which works on ASTs.
Okay, well, let's thank the speaker again.